3.1a is on compound inequalities. So there are two types, and or. The first type of compound inequality is and. So we are going to use our inverse operations to get the variable alone. So this is our process. Notice that this is exactly the same thing we've been doing all unit. The new part is we need to be sure we do the same operation to all three components. So let's take a look at a compound and inequality. So when an inequality is all connected like this, like either the number 1 or number 2, that's an and inequality. And what it's really saying is that our value x, right, whatever number it represents, it needs to fit into two numbers. It needs to be both greater than something and less than something. Okay, so it has two criteria it needs to fit under. So when we are solving these, let's take a look at number 1. We have 14 is less than 7x is less than 21. So it looks like a lot of stuff, but I'm going to start by splitting it up into 3 different sections. Right? So instead of having two sides like we would with any equation, we've got these 3 different sections we're looking at. Well, let's just focus on the section with x. We have 7 times x. Well, thinking of our inverse operations, the opposite of multiplying is dividing. So we're just going to divide by 7. The new thing here is that since we have 3 different sections of our problem, we are going to divide each of these 3 sections by 7. So negative 14 divided by 7 becomes negative 2. Well, 7x divided by 7 is just x. 21 divided by 7 is 3. X is isolated, so we are done with our problem. This is our answer. So let's write our final answer. We have negative 2 is less than x, which is less than 3. And that is our inequality. So again, we isolated x, which was our goal. So looking at this inequality, the potential solutions are the numbers that are greater than negative 2 and still less than 3. So we could have negative 1, 0, 1, 2. Those are the whole numbers that are greater than negative 2 and less than 3. So those are the numbers that satisfy this inequality. Let's take a look at number 2. It would be a good idea to pause and see if you can solve this one for yourself. Number 2, we have 0 is less than or equal to x plus 9, which is less than 17. So I'm going to do the same thing. I'm going to split this up into my 3 sections. And just looking at x plus 9, well, if I'm adding 9, the inverse of that is to subtract 9. Since I subtract 9 to one section, I have to do it to all the other sections. Okay? Well, 0 minus 9 is negative 9. X just stays x. 9 minus 9 eliminates to 0, and 17 minus 9 is 8. Well, x is isolated, right? X is all by itself right here. So our final inequality is going to be negative 9 is less than or equal to x, which is less than 8. That is our inequality. And again, our answers are any numbers that are greater than or equal to 9 and, greater than or equal to negative 9 and less than 8. They have to fit both of those criteria, right? It has to be this and this. That is why it's called an and inequality. Let's take a look at or inequalities. So or inequalities, still using inverse operations to get the variable alone. That hasn't changed. But we're going to solve each piece separately and then write the word or write the or statement at the end. So really it's like solving 2 individual inequalities and writing the word or in the middle at the very end. So let's take a look. Here's number 1. We have 2x plus 9 is greater than 17, or 5x plus 10 is less than 10. Okay. So notice how we have 2 inequalities. Here's a simple inequality. Here's a simple inequality. Okay, so basically we're going to solve one of the inequalities, then we're going to solve the other inequality completely separate from each other, and then we're going to write or in between our answers. So let's try this. I'm going to start off by drawing a gigantic line separating my problems. So 2x plus 9 is greater than 17. Well, let's subtract 9 to get 2x by itself. So we have 2x is greater than 17 minus 9 is 8. 2 times x is greater than 8. We can divide by 2 on both sides to get x is greater than 4. Well, x is greater than 4, x is isolated, so that's half our answer, so we're done with that part. Now let's go over and look at 5x plus 10 is less than 10, and we're going to solve this one. Subtract 10 on both sides. Well, we get 5x is less than 0. 5 times x is less than 0, so we're going to divide to isolate x. X is less than 0. That's the second half of our answer. So let's put all this together. So I'm going to write OR in really big letters in the middle of my answer. X is greater than 4, or x is less than 0. So solution to this could be any number that is greater than 4, or any number that's less than 0. So for example, 5 is greater than 4, but 5 is not less than 0. 5 is a solution because it satisfies one of these qualities. Okay, -2 is less than 0. It satisfies at least one of these qualities, so -2 is an answer. Let's see. 3 is not greater than 4, and 3 is not less than 0, so 3 is not an answer. So to be an answer to an OR inequality, it has to satisfy at least one of the two inequalities. Let's try one more. Now would be a good time to pause and see if you can solve this for yourself. I'm going to draw my line. We have 4v plus 3 is less than -5. So I'm going to subtract 3 on both sides. Well, we end up with 4v is less than -8. The inverse of multiplying is to divide. So v is less than -8 divided by 4 is -2. So that's the first half of our answer. Let's go ahead and find the second half. -2b plus 7 is less than 1. So let's subtract 7 on both sides, right? Because the inverse of addition is subtraction. So since 7 minus 7 eliminates to 0, we have -2v is less than 1 minus 7, which is -6. We're going to divide by -2 on both sides. So notice that we divided both sides of our inequality by a negative. Whenever this happens, the sign flips. So over here we have v is greater than, well, -6 divided by -2 is +3. We're going to write our OR, and then we're just going to put this together. Either v is less than -2 or v is greater than 3. And that is our inequality. That is our answer. Let's look at graphs for a couple seconds. So when we're graphing compound inequalities, if our graph is one long connected thing, it's an and then if it's got like this giant space between it, it's an or. So an and inequality is all connected. So our and inequality has the numbers 3 and 8. So I know 3 and 8 have to be in my inequality. And then x is going to be in the middle. So I'm just writing this one long inequality. I just have to figure out the signs. Well, 3 has a closed circle. So that means we have a less than or equal to sign. And then 8 has an open circle. So that means we just have a less than sign. Notice how these signs are facing the same way. That has to happen. You cannot end up with a compound and inequality where the signs are facing the opposite ways. That is gibberish. You can't do that. Okay? So 3 is less than or equal to x is less than 8 is our answer. Let's look at letter B. This is an OR inequality, so I'm going to write OR because I know that that's part of my final answer. So I'm just looking at this arrow right here. Well, this is saying that my answer is, my values are less than -5. So x, whatever x is, it needs to be less than -5. Or over here, we have an open circle on 1. So x needs to be greater than 1. Well, x is less than -5, or x is greater than 1. And those are our answers. This last one, well, this is and, since it's all connected, both closed circles. So we have -3 is less than or equal to x, which is less than or equal to 12. We could write this as 12 is greater than or equal to x is greater than or equal to -3. Those mean the same thing. Last little thing we're going to look at, we also want to be able to think about real life situations, so word problem type situations where we could represent things with inequalities. So letter A, the ages of the children in the class are 5, 7, 12, 6, 9, and 4. So if we wanted to represent these ages, there are a few different ways you could represent this. Let's represent this as an OR inequality. So I'm going to separate my ages into two groups. I have 4, 5, 6, and 7, and then I have 9 and 12. Okay. Well, we have a conspicuous 8 missing, so there are a lot of different ways to do this, but this is the way I'm going to do it. I'm going to say that our age of the children X can be less than 8, right? So that would be our 7, 6, 5, and 4. Or our ages X could be greater than or equal to 9, so that would be our 9 and our 12. So that inequality represents, or the ages of the children are solutions to that inequality. Letter B, again, it'd be a good idea to pause and see if you can figure it out. To get a B in algebra, you need at least an 80%, but it still needs to be lower than a 90. So look at this word and. We're going to have an and inequality. Right? Well, our lower bound is 80. So think about, it can be, you can have an 80% and have a B, so that's a less than or equal to sign. And then if you have a 90, that would bump you up to an A, so it has to be strictly less than 90. So to get a B in algebra, well, 80 is less than or equal to X, which is less than 90. So all of these are just looking a little bit deeper into our inequalities. Main thing you want to know is be able to look at an inequality and tell if it's or, since it has the word or in it, or it's all connected, so it's an and inequality.